Our speaker today got his degree, his bachelor's in geological sciences at Santa Barbara, and his PhD in geology at Arizona State in 2000. Josh Bandfield has been actively involved in spacecraft for some time, and these include the Mars Global Surveyor, the 2001 Mars Odyssey, the Mars Explorer Rover, the Mars Reconnaissance Orbiter, and the Lunar Reconnaissance Orbiter. His work especially focuses on atmospheric monitoring, surface composition, and thermophysical properties of planetary surfaces. He's currently a research assistant professor in ESS, and he started with us last February. His title today is A Complex Compositional and Aqueous History of Mars. Josh.
All right. See if we get the light so that we can actually see the screen. One of those permutations will work. Okay. Basically, I'm trying to cover quite a bit of ground with this talk, and hopefully I'll keep it general enough that kind of the interdisciplinary nature of the audience can follow it relatively easily. Basically I wanted to talk about essentially the slew of surface compositions that we see on the surface of Mars, and then do my best to try to attempt to connect that with what that means for the conditions in the past, and what that means for the ability for life to be preserved and develop on the surface. So let's just start with an outline of what I want to talk about. Essentially, basically these are what I consider sort of 4 steps, from basically collecting the data to trying to get at essentially why NASA is funding all the Martian orbiters and rovers to begin with. Is we're starting with collecting the data. We're trying to get at surface composition, and by the way, I'm going to focus on surface composition. There's also lots of morphological studies with cameras and other things that I'm going to largely not talk about. From the surface compositions, the reason we want to know these things is basically to get at the formation conditions. Basically, if you see a limestone, it means there's water there. If you have basalt, it means it was a volcano. Obviously, it gets a lot more complex than that. And then basically going from these conditions to linking those conditions to the habitability and preservation potential on Mars. And so, in NASA's mantra is basically, let's follow the water. We're trying to follow the water back to the conditions, back to trying to figure out whether or not life actually ever developed at one point and or still exists on the planet today. So, taking these 4 steps, I wanted to go over just a brief description of sort of where are we now. And basically, you can go from step 1, well, what I'm calling step 1, down to here, and it probably pretty much gets a little bit less, the amount of knowledge or data or understanding basically gets less and less as we go from the beginning steps down to the more complicated ones. But collecting accurate data, this is basically a whole bunch of NASA acronyms, and you can write whole paragraphs full of acronyms, but yeah, we've collected a lot of data. Mars Global Surveyor, Mars Odyssey, Mars Express, Mars Exploration Rovers, and Mars Reconnaissance Orbiter all have instruments on those spacecraft that help us try to understand what the composition of the surface is. And they've all been highly successful. They've collected terabytes and terabytes of data, and there's lots of data there with lots of potential. Taking the next step, well, we've got the data. Where are we with determining surface composition? And sure, there's many details that are still being worked out. There's probably many discoveries still left to be made, but many discoveries have already been made in the past decade. Basically, since Mars Global Surveyor went into orbit, our understanding of the composition of the Martian surface has changed in a big way, probably several times over now. Okay, getting a little bit more specific, let's take these surface compositions and try to interpret what the formation conditions, what conditions were present on Mars at the time. And that's actually more difficult, of course. And hypotheses have been forwarded, and links are starting to be made but I would argue that basically our understanding is getting more and more vague. And then finally, this final step of linking those conditions to habitability, the way I would describe it is it's no longer exclusively the realm of wild speculation. Essentially, there's actually good work that's starting to be done there, but the amount of unknown versus the amount of known, it's a very large ratio. So let's start with the measurements. And I'll describe, hopefully very briefly, the measurement techniques. And I'll focus mostly on, essentially, the spectroscopy. Basically, my expertise is in thermal infrared spectroscopy, and basically a lot of the compositions that we know about the surface of Mars today are visible through thermal infrared spectroscopy, both from orbit and in situ. And that's going to be the primary focus presented here. But one thing I wanted to make sure I pointed out is that other measurements have been made, and they made very important contributions. Basically, Mossbauer spectroscopy, which the Mossbauer spectrometer is on the instrument deployment device on the Mars Exploration Rovers, has given us vast amounts of information on the iron mineralogy of the Martian surface. So that's made a very important contribution that I'm not going to talk about in detail. And then there's gamma ray, neutron, alpha proton X-ray spectroscopy. Basically, those give you elemental compositions, either from orbit or in situ. And basically, with those compositions, you can infer surface mineralogies as well. And they've made really important contributions as well. The big point here, though, is that no single measurement technique provides a complete mineralogical picture. You have to look at something from a variety of perspectives in order to get at basically what is the mineralogy of the surface. And some techniques are better under fine-grained for fine particulates. Others are better for coarse particulates. Warm temperatures, lots of sunlight. Basically, different conditions are better for different instrument techniques. And so even though the principal investigator of any one of these instruments will tell you it's the greatest thing since sliced bread and that it will tell you everything you want to know about Mars, basically it's a combination of the measurements that helps build up a good picture. So let's start with thermal infrared spectroscopy. And this is basically the one slide background. And this is where I've focused much of my work. We're looking at 5 to 50 micron wavelengths. Basically, we're looking at energy that's being emitted from the surface. It's not reflected light, it's emitted light. And if we look at emissivity, basically the way I'd put it is basically different materials glow different colors in the thermal infrared. And these are a variety of different rock-forming minerals, from quartz to feldspar, clay, pyroxene, and olivine. We're going from isolated tetrahedra to framework silicates, as well as carbonates and sulfates. And you'll notice that the squiggly lines are very distinct between the different materials. And so basically, these different materials have their characteristic fingerprints that you can use to identify what the composition of the surface is. So most rock-forming minerals have these distinctive absorptions in the thermal infrared. And one of the nice properties of this is that if you're looking at a coarse particulate surface, like sand or rocks or whatever, essentially the contribution to your measured spectrum combines in a linear manner. So you can basically use that to deconvolve your measured spectrum to back out the abundance of each of the constituents. So if you had the basalt, for example, you'd have basically the pyroxene and the feldspar and the olivine would combine in a linear manner, and you could take that spectrum of that basalt and deconvolve the weightings of each of these spectra to get at the abundance of them. Of course, that has many, many caveats and other issues, but to first order, it works pretty well. And so fine particulates, so if we're looking at the Martian dust rather than Martian soils or rocks, have a very different set of sensitivities. And so things go very nonlinear, and we become more sensitive to things like carbonates and less sensitive to things like pyroxenes. So there's a very large set of rules that goes along with it.
And why is that in that particular example?
Essentially, with coarse particulates, you don't get photons basically going through individual grains. Once you get below about 50 microns or so, basically the photons will start passing through multiple grains, and so the scattering, you get volume scattering. Okay, looking at visible and near-infrared spectroscopy. So now we're looking at reflected light, basically just like you see with your eyes. And there's no set and hard definition for wavelength ranges, but I'm just going to arbitrarily define it as about 0.4 to 4 micron wavelengths. And this has a whole unique set of sensitivity that's highly complementary to the thermal infrared. Essentially, we're sensitive to iron 2+ and 3+ electronic transitions, very sensitive to OH, H2O, and carbonate vibrational overtones. And you have a high sensitivity for a certain set of compositions and particle sizes, and the behavior tends to be highly nonlinear. So in this case, you can detect things like very small percentages or abundances of phyllosilcates or clays present, but on the other hand, you wouldn't detect quartz or feldspar. And basically, these are some of the different types of minerals that you can detect. There's augite, and these are the iron 2+ absorptions. Nontronite, which is a phyllosilicate, has these 1.4, 1.9, 2.3 micron absorptions. Hematite has the Fe3+, iron 3+ absorptions. Gypsum has water absorptions. Calcite has the carbonate absorption. So these all have their distinct signatures that are very easy to distinguish from one another. So I'm going to start with basically this step here, collecting accurate data. And I want to go over some of the different instruments that have been flown on the different spacecraft, basically to give a sense of what kind of data is being collected and what it's capable of doing. And the first one I'm going to start with the thermal infrared because that's my bias. This is the Mars Global Surveyor Thermal Emission Spectrometer, and it's a Michelson interferometer, basically 2 orthogonal mirrors and a beam splitter. You split up the light, you combine it again, you get interferograms, and somehow you can magically transform that into radiance versus wavelength. It is a spectrometer, not an imager. So this is the type of data that we get out of the TES instrument from about 60 to 50 microns. And the line basically shows a bunch of different things. And if you're attuned to what's going on here, you have the CO2 absorption. This is atmospheric dust, minor CO2 bands, water vapor. And this double hump right here is basically the hematite that was found in Sinus Meridiani. So if we try to make out an image from the data from the TES instrument, you can basically build up crude images with these strips. You don't have very good resolution, about 3 kilometers per pixel. But you can locate on a map the location of these unique spectral features. And I'm showing this sort of for historical purposes because once as a grad student I spent about a full week putting this image together to try to map out where the hematite was.
So when we see a hematite map, like when they were deciding where to put the rover down, it's really the strength of that feature that's being mapped.
Generally, it's the strength of that feature. You can do a little bit more of that deconvolution thing where you try to get the weighting of the shape in the spectrum. But yeah, essentially what you're looking at is the strength of that feature. And I'll show another image later on that shows a more detailed map. The other orbital thermal instrument we have is the Thermal Emission Imaging System. This is Emiss. It's on the Mars Odyssey spacecraft. And the combination of TES and Emiss is actually a very nice combination. One is a spectrometer with low spatial resolution but high spectral resolution. Emiss has high spatial resolution, 100 meters per pixel, so we can collect reasonable images of the surface, but it has low spectral resolution, and we're only looking at basically 9 different wavelengths between about 7 and 15 microns. So whereas we were building up crude pictures but nice spectra with TES, we build up nice pictures but crude spectra with Emiss. And this is an example of Emiss data. This is an infrared image of a crater off in northern Syrtis Major. And the boxes basically represent the locations of the spectra that were plotted over here on the right. And you can see that basically the colors show some co-located different spectral surfaces. In this case, we have a surface with strong spectral features at short wavelengths, which is indicative of a high silica content. And indeed, if you look at TES data, it shows that this area right here is composed of basically quartz and feldspar, which is generally, it's basically a granite on the surface of Mars. The third thermal instrument is the Mars Exploration Rovers mini-TES. It's also a Michelson interferometer, just like TES. It's like TES, but mini. And essentially, it's sitting there on the surface and can collect spectra, and these dots here basically represent the spot size of what we're capable of resolving. This image here, it's a little bit faint, but you'll see that warmer colors like reds basically represent warmer surface temperatures. Cooler colors like blues represent colder surface temperatures. And for each one of these spots, we're collecting a full spectrum with which we can use to try to characterize the mineralogy of the surface. Okay, almost done. We've got 2 more instruments. Mars Express Omega. Omega is a visible and near-infrared, actually I think it's just a near-infrared, no, it's a visible and near-infrared spectrometer, Whisk-Broom's grading spectrometer, and this was probably what I guess I would consider sort of the first high-quality visible and near-infrared spectrometer to go to Mars, certainly with a complete data set. There was one on the Phobos spacecraft back in 1990, but it collected a limited amount of data. And so we can create crude images with about 500 meters per pixel spatial sampling at periapsis. Mars Express is in actually quite elliptical orbit, so if you're looking at Mars from farther away, it's going to be a larger pixel size. And you can build up pictures with the different spectra. So we're taking full spectra at high spectral resolution and sort of a reasonable spatial resolution. And in this case, we're showing essentially data that shows the difference between different iron 2+ absorptions with olivine, low calcium pyroxene, and high calcium pyroxene, and you can see the how they're spatially distributed on the Martian surface. For scale, this is 2 degrees of latitude, and a degree of latitude on Mars is about 60 kilometers, so it's about 120 kilometers from here to here. And this is from Pelkey et al. It's being cut off, but I'm trying to reference things when I show other people's work. And then finally, we have the Mars Reconnaissance Orbiter Compact Reconnaissance Imaging Spectrometer for Mars. Basically, this is the CRISM instrument. It's a push-broom grading spectrometer, and this is essentially a very high-quality data set that gives us 18 meters per pixel spatial sampling with 544 spectral channels from 0.3 to 3.9 microns. So essentially, this is what we're trying to get at with TES and Emiss, but you've got in the with the visible near-infrared is basically both high spectral resolution and high spatial resolution. And it's easier to achieve this when you're looking at shorter wavelengths because of the optics don't need to be quite so large, and you can save weight. So basically, we can collect pictures, highly detailed pictures. This is about 11 kilometers across, and what we're mapping here is basically the strength of this absorption right here. Actually, we're looking at the strength of this absorption right here, which indicates hydrated silica strength absorptions on the surface, and we can map it out in high detail. And this is the same crater that I showed from the Emiss image, where this was the location of feldspar and quartz. And what CRISM is seeing is not the feldspar and quartz because it's not sensitive to it, but it's seeing the hydrated silica. So that it gives a sense of the complementary nature of the measurements. Okay, so we've got these different spectrometers. We've got a whole bunch of data from different wavelengths and different resolutions, and getting at the surface compositions of the surface and then interpreting those formation conditions is sort of the first point of what we're trying to do, or at least what I've been trying to accomplish. And I'm going to start with essentially what Jean-Pierre Bibring et al. In 2006 proposed in a paper that came out in Science, and it was titled, in somewhat of a grandiose manner, Global Mineralogical and Aqueous Mars History Derived from Omega Mars Express Data. So the near-infrared spectrometer on Mars Express has determined the surface composition in a manner with which we can basically recreate the aqueous history of Mars. And he broke it down into 3 compositional units, which were then interpreted to be from 3 different eras of aqueous alteration. So, and these were the 3 compositional units: phyllosilcates, sulfates, and ferric oxides. Now, phyllosilcates, and generally they form with lots of liquid water, and they were generally found in older terrains on Mars, what they call the Noachian era. So, and this was interpreted as sustained aqueous alteration of materials during the Noachian. So this is greater than 3.7 billion years ago, plus or minus quite a few million years in terms of error. And then the second part of this was that it at some point, Mars changed its global aqueous environment from something with relatively moderate to high pHs, and we had a volcanism-driven sulfur source. Volcanoes basically release lots of sulfur, sulfur-rich gases, and that could create an acidic environment which would change the global aqueous chemistry. This happened during the late Noachian, throughout the Hesperian, and any water that was present would, as it dissolved things in the rocks, it had lots of sulfur dissolved in it, it had lots of magnesium and calcium and other things, and when it evaporated away or the conditions changed, it would precipitate out sulfates. The third era was characterized by limited availability of water during the Amazonian. This is less than 2.9 billion years old. And it results in basically a dominance of what Vibring proposed was gas-solid weathering. So this was the three eras, the three compositional units, and some of it I actually agree with quite, basically the phyllosilcates, that's a very important discovery. It shows that there was a lot of water. They do appear to be concentrated, though not exclusive, to the older terrains. Whereas other aspects of this, such as gas-solid weathering, which has never actually been shown to actually happen, or the sulfates, which is driven by this volcanism source where we know there's lots of volcanoes on Mars, but we actually don't really have much idea about how much sulfur they actually released or actually when that ever occurred. So some things are actually quite a bit more vague, and I feel sort of need some closer scrutiny.
Josh, are you going to talk about where these ages come from?
I wasn't. The general ages come from, okay, so Mars was split up into sort of three different eras, Noachian, Hesperian, and Amazonian. And Noachian is sort of the heavily cratered old surfaces on Mars. Hesperian is associated with Hesperian ridged plains, basically after the heavy bombardment, and characterized by lots of volcanics and basically wrinkle ridges. And then Amazonian is sort of postdates that. So they're related to sort of three different global morphologies on the surface.
Right, so these are correlations of composition with these morphological features, in particular crater counts.
Right.
Where ages have been estimated.
As well as could be done with the data that was available. And in fact, what Vibring ended up doing was creating his own Martian timescale and reset the different dates. So there's sort of the Vibring et al. Timescale, and then there's the traditional Mars timescale, but they roughly correlate with one another.
Richard, just turn off the front lights.
How do I do that?
You'll see it now there. This is board light or something like that.
Lecture.
Full note.
Lecture. Oh, sorry, demo.
Demo. Demo. Oh, nice. Thank you. Okay, so going over those three different compositions, we have phyllosilcates. And once again, we're showing CRISM data. CRISM has some beautiful images showing in extreme detail the distribution of phyllosilcates on the Martian surface. Once again, it's about 11 kilometers across. This is an area called Nili Fosse, which has also high olivine concentration surfaces. But essentially, the phyllosilcates are found in Noachian terrains, the older terrains. And remember that the phyllosilcates require generally a moderate to high pH of water to form, and they will not necessarily form in an acidic environment. Otherwise, the formation environment remains actually quite unclear, and that's one of the concerns for the Mars Science Laboratory landing sites. A lot of them are proposed to be in phyllosilcate-rich terrains, and yet one of the problems has been getting the geologic context of exactly what was going on. Was this a surface or a subsurface formation environment and things like that. And then the concentrations, although this shows, nice, sort of blood red, high concentrations, the concentrations can actually be quite small. And in most cases, they're probably less than 10 or 15%. There's some argument over the strongest concentrations. But in general, they're low concentrations. And one of the reasons we know they're low is because the thermal infrared measurements actually don't detect them. And the major groups, it's not just, okay, so we've identified phyllosilcates, but phyllosilcates, if you're a geologist, you can split this up into different groups of phyllosilcates, and each one of those groups can be split up into even different specific types of phyllosilcates. They've actually identified illites, chlorides, kaolinites, serpentines, and smectites. I think it's just the dioctahedral, not the trioctahedral smectites. But a variety of different phyllosilcates have been found, which indicate different source compositions or even different formation conditions. And this gives us sort of a global distribution of what's been found. So these little boxes basically show where they've identified them. However, their boxes don't represent the actual areal coverage. The actual area coverage on the surface is much, much, much less than 1%.
What are the colors in this?
I don't know precisely. Essentially, they're describing the different types here. Although I don't
Topography.
I'm sorry?
It's topography, so it's altitude. And
Oh, the colors of
boxes.
yes, this is a topographic map in the background.
Okay.
Sorry,
Okay,
I thought you meant the colors of the boxes. So yeah, the volcanoes, Olympus Mons, Tharsis volcanoes and such, and Valles Marineris. Second composition, sulfates. This is a picture from the PanCam in Meridiani. I think this is Victoria Crater, showing the outcrop rocks that I'm sure you've all seen pictures of. Beautifully cross-bedded, essentially sandstones. And these are chock full of sulfates, as well as pyroxenes and silica and feldspars. But essentially, we see lots and lots of sulfates in places like Meridiani. And there's many occurrences within equatorial layered deposits throughout sort of the Valles Marineris region of Mars, throughout Meridiani region. Essentially, they occur widespread, even if they're sort of isolated, throughout equatorial Mars, with one exception of this really strong deposit that they found right next to the North Polar Cap. So you don't see sulfates anywhere outside of equatorial Mars except for right next to the polar cap. And what it's doing there and why it's there is sort of anybody's guess at this point. So the compositions include various hydration states of calcium and magnesium sulfates, indicating different cations. And basically, the hydration state is very sensitive to the temperature environment. So you can basically get at what the history of the sulfates have been in recent climate history. And of course, as I showed, they're found by rovers in both Meridiani and in Gusev. And what's really interesting is despite the widespread high concentrations of sulfates that you see in Meridiani, we're talking 30 or 40% in some cases, they're not detected from orbit. We're confident that they're there, and yet you can't see them from the spectrometers from orbit, even though it can be resolved. So that's one note of caution about when you look at the orbital data, when you're not seeing something, it's not necessarily telling you much. And in the case of Meridiani and Gusev, it's the only detection of jarosite, which is an iron sulfate, which indicates acidic conditions. So when you see sulfates, you don't necessarily think, okay, this had to be an acidic environment. You can form calcium and magnesium sulfates in relatively normal environments, but when you have things like iron sulfates is when you can start to say something about the actual aqueous conditions in terms of the pH.
So what's the best guess as to why you don't see it from orbit?
I'm at a complete loss, actually. I really don't know. I mean, you can always argue textures or particle sizes or interference from other different compositions, but that's all hand waving. And then finally, the third type is ferric oxides, and as simple as you can put it is Mars is red. That's been known for a long time. You see that red color of the surface, it looks like rust. Mars is sort of, in a way, rusted. But one of the interesting things is that the actual weathering process actually remains a little bit unclear. You have these ubiquitous nanophase iron oxides. It generally implies very limited amount of liquid water. And one of the questions is, how much water is necessary? Can you get adsorbed layers that actually make this process occur? Do you have to have actual amounts of liquid water, or can this be in a bone dry environment? And it's actually still not really well known. So there's our three compositions that have been proposed as sort of describing the global aqueous and compositional and aqueous history. But essentially, I'm going to go over some other things that you can add to this, and I would argue that there's a lot to add to this history. So the first one, hematite, which I mentioned before, and this is as well as you can do with the test data in terms of mapping the detailed distribution. Hematite is a relatively unique composition. Those blueberries that you see at the Meridiani site, that's the source of the hematite. And there's occurrences in a bunch of different areas: Meridiani, Arum, Orium, and Ion chaoses, Ophir and Cantor chasmas, as well as Hebe's chasma. They all have identical spectral signatures, and they're all associated with the more extensive sulfate-rich deposits. So these are layered terrains, and the hematite seems to be associated with a relatively thin layer of maybe 50 or 100 meters within a much more extensive stack of deposits. And so I'm not sure anybody really knows what it means, but in terms of what it seems to be saying to me is that this might be indicating periodic episodes of a unique aqueous chemistry throughout much of Martian history, because these different areas seem to span quite a range of ages, from late Noachian to early Amazonian. Silica. There was an article that just came out in Geology this month on the discovery of hydrated silica on Mars, which we've discovered a number of times over at this point. We have silica phases in a variety of forms, from quartz to hydrated or dehydrated amorphous silica, in terms of coatings or actually bulk compositions. And they seem to be forming in a variety of different geological situations. In different locations: home plate, Aqueous crater, Western Hellas Basin, Meridiani, Northern Lowlands, Cirrus Major, Ninetales Menzae, Valles Marineris, and the list will probably continue to grow. And they seem to fall into two categories, if I wanted to categorize them. And one is in the terms of coatings. Essentially, silica coatings tend to form, and it's very common on desert surfaces, to get basically a coating of more or less amorphous silica on any sort of rock, like a basalt or whatever. And then in other situations, you'll see high concentrations. This is silica in the Columbia Hills. This is basically the rover dug up some stuff that was buried, 90% by weight SiO2, which pretty much indicates that you have much more extensive aqueous activity. You have these yellow deposits here. This is in Western Hellas Basin, where as best as we can tell, it's about 75% high silica phases, which indicates a surface that's probably on the order of 80 to 85 to 90% silica content. And so these deposits indicate that it's not just a coating, it's probably a much, much more extensive aqueous activity. In some cases, the best guess is a hydrothermal deposit at Gusev. Another composition is zeolites. As well as I can describe it, hydrated tectosilicates. Essentially, basically, you take a framework silicate and add water to the structure, and that's what zeolites tend to be. They're usually found in altered volcanics, and they usually form from interaction with alkaline groundwater. And there's a whole slew of different zeolite compositions. And what's interesting is that even though it's its own class of mineral type, and it's been seen in a number of locations, nobody's really done a whole lot on it yet. There's little bit that's been mentioned besides the presence. And you'll read these papers, and it's like, okay, here's the zeolites and the phyllosilcates or whatever. And they don't tend to dwell on the zeolites, maybe because we don't know what to say about it yet. Once again, this is that crater with the quartz and feldspar surface with the hydrated silica. And up on the central peak, you can see basically high concentrations of those zeolites that are present. So yet another compositional type. Carbonates. So we're going through the list, and I'm going to get tired of talking at some point. This is in the moderate to high albedo regions of Mars. There's a spectral feature in the test data, and it's this spectral feature right here. Essentially, carbonates have a strong absorption at 7 microns, and in the fine-grained particulates, it's actually sort of like throwing a little bit of black carbon in snow. You can make a very big effect with a very little amount of the substance. And you have this solar shoulder here, which is very diagnostic of the presence of carbonates mixed in with silicates or oxides or other materials. And the dust spectra indicate about 2 to 5% carbonate by weight. And this distribution is ubiquitous. So basically, throughout all of Mars, on all moderate to high albedo regions where you're sensitive to this type of thing, we see a little bit of carbonates. And what's really interesting is that the Phoenix lander is one of these areas that shows this type of signature. And what's been coming out in the last couple of weeks is that they're seeing, what do you know, a couple of weight percent of carbonates. If I remember right, they're actually saying sort of like 5 to 10%. But it's showing similar results, which I'm very happy to hear because it seems to be pretty consistent. So one thing about the carbonates, the presence of carbonates, and I was arguing with Conway last week about this, but I like to push the whole atmospheric buffer mechanism. Essentially, if you have a carbon dioxide atmosphere and you have other unweathered materials, what you're going to do is draw down the CO2 from the atmosphere when you weather those materials to form the carbonates. And that mechanism will proceed until liquid water is no longer stable, and then that will shut off or slow down considerably. So it's a nice, it sounds nice at least. It's a nice, I like the hypothesis is put forward by Ralph Kahn way back in 1985 to sort of explain why the Martian atmosphere is close to the triple point of water as it is right now.
CO2.
Yeah, sorry, yeah. Okay, widespread dissolution of olivine. This is sort of almost a negative result of one thing that we're seeing across the planet in a lot of different locations, and it's best shown at Gusev Crater. This is the rock called Adirondack. The Adirondack on the interior has a high olivine content. The exterior has a weathering rind with a low olivine content. And all of the rocks in this region all have the same composition. They're all Adirondack class rocks throughout the Gusev Plains. Not in the Columbia Hills, but throughout the plains. Now the soils basically have very low olivine contents. And so there's a progression of high olivine content down to low olivine content. And this is indicating that, well, olivine is going away as you're basically mechanically processing this stuff from rocks into soils. And we see the same pattern over and over again across Mars, where you have high inertia, basically rocky surfaces that have high olivine contents, and the surrounding soils have low olivine contents. And this is consistent with basically limited amounts of water dissolving away the olivine and forming iron oxides, silica, and sulfates. And what's interesting about this is this actually might be a widespread process, and it's sort of a global process, and yet it's not really recognized as a process which it's not recognized that water has played much of a role across much of Mars' surface. We're usually focused on these isolated phyllosilcates or sulfate sites, and yet this might be actually much, much more common than what we realized. Chlorine distributions. This is, okay, so getting away from spectroscopy a little, from the visible to thermoinfrared spectroscopy and looking at the gamma ray spectrometer. This is an orbital instrument on the Mars Odyssey spacecraft, and it gets elemental composition, sort of 600 kilometer resolution, and it's better at some elements than others. One of the elements it does very, very well with a high signal noise and resolution is chlorine. And there's some strange chlorine anomalies, basically strong chlorine surfaces with high couple percent, basically a couple percent above the background chlorine abundances, covering relatively large areas of the planet. And so the highest concentrations happen to be coincident with the Medusa Fossae formation, which is basically this. You can actually see it topographically on the map. Some of these mounds here are parts of the Medusa Fossae formation. And that these are coincident with this formation that generally gives us the impression of being a vast ash deposit, volcanic ash. And so the question is this a product of a unique alteration, or is it a unique source composition? And we don't know one or the other, but the high chlorine contents is suggestive of some kind of aqueous process that could be occurring regionally on Mars that we're not really detecting otherwise.
For this astronomer, could you just talk about chlorine geologically? I mean, I think salt, of course.
Yeah, and that's generally what you would think is salts like halite, table salt or whatever, evaporites.
Are there other things that chlorine is common in?
Not common. Because it's so soluble, it'll dissolve away really quickly, and then the only way that you get much out of it is when you evaporate the water away, and you'll get the salt deposits. Charlotte will correct me later on, probably, but another thing out of the gamma ray spectrometer suite of instruments. This is actually from the neutron spectrometer. Equatorial regions are showing areas that are equivalent to, I can't remember the number, sort of 15 to 20% by weight water that might up to. So basically, in equatorial regions, we're getting high hydrogen signals. And from the measurements, they're indicating that they're probably buried a couple centimeters And what's interesting about this is in equatorial Mars, water ice is not at all stable. It's not going to stick around for a long while. You can probably construct situations where you can actually seal it off and keep it from evaporating out to the atmosphere. But I think most people generally agree that essentially this is consistent with hydrated mineralogy. So if you had a hydrated magnesium sulfate, for example, or even zeolites or phyllosilcates, the most consistent is very hydrated magnesium sulfates. So you have this vast area of Mars. This is, thousands of kilometers in diameter here. And it's by far the most extensive deposit of hydrated minerals if you do buy that argument. And what's really interesting about this is we're not detecting any of it from orbit with the reflectance or thermal infrared spectrometers. So we see this huge water deposit that we're associating with hydrated mineralogies that we're not detecting via any other means. And one of the things that makes you sort of think about this being more extensive is this is off in the Columbia Hills. And as you drag that rover, one of the wheels isn't working very well, and it basically kicks up and stirs up all the soil. And before this was chewed up, it looked like the rest of the surface here. And after they drove by it, there's all this bright material. And this bright material is extremely sulfur rich. It's basically sulfates that were just buried right underneath the surface and not at all seen before they kicked up and stirred up the surface. And so it looks like you can bury things on Mars just a few centimeters and very extensively. And we're not really quite sure what that process would be. Okay, a couple more things. Columbia Hills. So in general, I just wanted to talk about the Columbia Hills and Gusev Crater. And this is from Ming et al., and this is Douglas Ming, and this is Dick Morris et al. From 2006. This is Dick Morris's classification scheme for Gusev Crater rocks. So we're looking at just a couple hundred meters of a traverse on the Columbia Hills, and all of a sudden we have Adirondack class, Peace class, Backstay class, Clovis, Wishstone, so on and so forth, with all of these different basically elemental compositions that indicate from minor alteration to highly altered. Basically, we have this huge variety of different rock types indicating different types of alteration, all within this tiny little area within a little spot of Mars that we don't detect at all from orbit. So this is almost as if you took the entire complexity of Mars as we know it right now, put it in a blender, and deposited it in the Columbia Hills. And basically what this is basically just sort of a humbling thing saying that, okay, there's all this stuff that we're not detecting, and this is just a glimpse of what might actually be going on Mars.
What's the emphasis on?
I'm sorry. That's a good question. This is sulfur, chlorine, and bromine.
Fe3 plus over Fe total.
Okay.
But now, is this greatly surprising that when we get the detail, we find out it's really pretty complicated? I mean,
that general trend is not surprising, but just the vast degree of what we've seen in such a small area, and just our total ignorance from the orbital observations, that's what's surprising, I think. Just sort of the extremeness of it.
or another way of asking it is for a typical area on the Earth, is it less variety? I mean, on Earth we compare it all the time, of course, ground truth, quote unquote, with satellite stuff.
Well, it matters where on Earth. I actually would argue that in general, if you took any piece of ground on Earth, you're not going to come across something like this. But then again, Gusev was a really dull place until they actually got to the Columbia Hills. So it's sort of like you're walking along sort of a valley fill on the Earth, and then all of a sudden you come across Cuprite, Nevada, with all of its hydrothermal and other stuff going on. And I think I'm at the final composition, chlorides, with a big question mark right next to it. This has been seen with the Emiss data. It's characterized by low emissivity and interesting sort of fractured patterns. And there's hundreds of exposures within the Milwaukee and Southern Highlands. There's other explanations possible, and I mainly put this up just because there's new things coming up that we're not understanding that actually might be a very important part of this entire picture. However, if they are chlorides, like halite, which is just basically table salt, that's a whole new sort of aqueous class of minerals. That's sort of a pattern that should be recognized throughout Mars. Okay, so let's go back to our Martian compositional history as it was proposed, or I'll call it version 1.0. And we've got our phyllosilicates, sulfates, and iron 3+ weathering. And so this is as best as I can come up with, and it's actually really complicated, and I actually don't think I understand it very well at this point, but I'm not sure anybody does. So if I was to try to make a new version of this, this is sort of the best thing I can do, is basically here's my version 1.01, where I modify some of these things, like associate amorphous silica with the sulfates, and silica coatings and olivine weathering with the iron 3+. This is sort of basically, okay, yeah, this is much, much more complicated. And that's the point. It's not that you should trust any one of these lines, because I'm not sure I trust myself, which is the reason why there's so many question marks here. But the little bit I think that we do realize is that this is an entire planet with an entire sort of real complicated set of different aqueous systems. And the next point I wanted to make was basically, this is point number 2, variable formation environments. And there tends to be this thinking of, okay, I'm seeing sulfates here, so I must not see phyllosilcates because they don't form in the same conditions. In the first order, that's sort of correct. And that's actually as well as I understand it myself. But you go out into the real world and you see basically phyllosilcates right juxtaposed right against sulfates. Phyllosilcates and sulfates are not mutually exclusive on Earth or Mars. And so they can be forming contemporaneously and in close proximity to one another. So this is, Alice Baldridge gave me these pictures. This is Lake Gilmore off in Western Australia. Out in the middle of the lake, we have low pH environments where we're forming nice, beautiful sulfate crystals. And if we go over to the edge of the lake, we have a moderate to high pH environment where we're forming phyllosilcate-rich materials. And so this is sort of the type of real-world situation that really does occur and is likely to have occurred on Mars as well. Okay, so the last, and hopefully relatively quickly, going off to linking conditions to habitability and preservation potential. So I actually wanted to make this relatively applicable to sort of the astrobiological focus here. And in doing so, I want to caution you as to what I'm about to say. I don't typically, this is where I know the least, to put it bluntly. And so I'm learning about this stuff. You go to the Mars Science Laboratory workshops, they basically, that's probably the goal of the mission, is to try to find habitability. And so I'm learning about how the minerals themselves relate to what conditions were and then how well life would do there and be preserved. And so the first thing is in habitability is, okay, this is what we've always been told. Liquid water. You need liquid water for life. And so that's the first thing, that's the first question you ask. And that one's simple. I think I understand that one. It requires mineralogical evidence, basically of clays, sulfates, carbonates, a lot of the things that I've been talking about. These things imply the longer-term presence of liquid water. So if we had water washing across the surface for a little while, you probably wouldn't see much of a signature of it, but if it was around for a long time, you can dissolve a lot of stuff and then precipitate it out again and weather things. And the other aspect of this is morphological evidence, which I'm not going to dwell on too much, but there's plenty of morphological evidence as well on deltas, shorelines, channels, layers, and you look for evidence of sustained activity, like meandering stream channels or sedimentary sequences. And optimally, you'd like to have both. And so this is Evertswald crater. This is interpreted as basically reverse topography in a deltaic deposit. And there's signatures of increased hydration along the edges of this deposit. So this is one of the proposed Mars Science Laboratory workshop landing sites.
What is reverse topography?
Essentially, if you deposited more resistant material within a channel and then you eroded all the other stuff around it.
So a higher area shows you where a stream was.
Yes, exactly.
So is that hydrated sulfates, phyllosilcates?
I believe it was phyllosilcates. Technically, what we're looking at here is essentially the Ralph Millikan's. He determines the water content of a surface by looking at the 3-micron absorption, and that's technically what's being mapped here. But I think he attributed it to phyllosilcates. These are actually quite small abundances. You're going from like 3% to maybe at the most 10% hydration. So taking this habitability question and asking some second-order questions, or maybe first-order questions, besides the whole liquid water one, is you want to look at the oxidation, pH environment, energy source, nutrients, and water activity, amongst probably many other things. And Dave Desmarais put this into a nice little simplistic thing that I could understand, and thinking of just what you call a habitability box. Essentially, you want nutrients, but if you have too few, you'll starve. If you have too many, it's basically a toxic environment. You can't have too much energy. Well, things don't survive very well in a fire. But if there's no energy to harness, well, you're not going to have much to live on. And then water activity, there can be too little, or you can just dilute it too much. And one thing that I really sort of grasp onto is this whole water activity concept, which is something that can be actually very nicely related back to the mineral composition of a surface. And this is summarized from Nick Tosca, had a paper that came out in Science this year, where he basically looked at the geochemistry of the Martian surface as we know it, or as we can presume it might be, and tried to basically understand what the water activity was, what the water activity was in the environment. And water activity is essentially the chemical availability of the water. For example, increasing the salinity of the liquid basically decreases the water activity. And if it's too saline, you're not going to, basically life won't be able to survive. So he's got a couple of different points. He uses the Martian compositions to predict the water activity. And this is a very important part of it, is he argues that brines are not remnants of dilute waters that evaporate subsequently. And I think you can still argue with that point quite a bit. But his argument was these didn't start out as dilute, nice lakes that you could live in very happily, and then basically evaporated away. He's arguing that, for the most part, in the deposits that we see, the water was concentrated pretty much from the get-go. And then he distinguishes, this is the other important point, he distinguishes between originating in and adapting to a low water activity environment. And essentially, his argument is that low activity of water inhibits prebiotic chemistry. And so if life were to try to get started, it would not do so very well in a low water activity environment. And so we have our, essentially the chemistry of the water, the activity of the water on different situations. This is Meridiani planum, the sulfate deposits in Meridiani. This is the Noclites. These are Martian meteorites, which have some evaporites in them at low concentrations. And this is Earth's seawater. So he calculates basically the activity of the water in the different situations. And to summarize that in the chart, we have the water activity values for the sulfates at Meridiani, chlorides at Meridiani, Martian meteorite brines, and Paso Robles, which is in Gusev Crater of the Columbia Hills, soil brines. And comes up with these numbers for water activity, which are actually quite very low. And for comparison, if you're looking at Earth organisms, the limit is 0.9. For extremophilic fungi and archaea, 0.75. And the actual limit, the record, is 0.61. So I'm not necessarily saying that this, life will never develop on Mars because the water activity is not good. But the basic point is, this was a really nice concrete example of where I can take the mineralogy of Mars and directly apply it to how life would develop and or survive on the surface. The second point, and I'm almost done, is preservation potential. So not only do you have to have habitability, but whatever you grow in this environment has to stay there for you to discover it later on. And so that brings up a whole new set of conditions to consider. Once again, water activity, but instead of a high number, you want a low number to preserve it. Essentially, you want to pickle something. Permeability, are you able to wash it away? Temperature, if you bury it too deep, you're going to basically decompose things. Oxidation potential, you generally don't want to oxidize it, so you don't want it exposed to, say, UV radiation right at the surface of Mars. And then exhumation, you want it to be exposed at the surface. So you want it to be at the surface, but not for too long. And this is cut off at the bottom here, but basically it's like this is a whole new set of conditions that you need to look into in order to basically figure out, okay, where am I going to go on Mars in order to find any remnants of life? And the mineralogy of the surface not only has something to say about the habitability, but also whether or not it's actually preserved. And so essentially to conclude, the conclusion is sort of a non-conclusion. It's basically stay tuned. We've got a wide variety of compositions on the surface. We're starting to understand it much better. It's a growing list. And what I think it tells us is that there's a variety of co-temporal aqueous environments on the planet. That shouldn't be a surprise, but it's something that we should be very aware of. And then much remains to be discovered and more fully characterized, as I said. So the big question is, where is habitability and preservation potential maximized? And that's why I want to talk about the Mars Science Laboratory here, is basically the landing site selection process has been all about this question. And much of it revolves around the morphology of the surface, but much of it also revolves around the mineralogy of the surface. So taking the mineralogy of the surface, the composition, to try to answer this question, to figure out where to send the $1.8 billion lander and growing, is basically the question to ask, and that's why this stuff is important. And I think I'm going to stop there. So thank you very much.
Questions?
Eric?
You mentioned that when you were talking about the different detectors, and you were pointing out that CRISM has sort of the optimal thing in that it's high spatial resolution with high spectral resolution, but the trade-off is you get a really small area that you can see. How long will it take for CRISM to map the entire surface?
Essentially forever. CRISM, they've done a couple of neat things, and that's always a trade-off. And how many bits can you send back to Earth as well? And MRO's got this nice, big, huge antenna with just a wonderful data rate. They also have essentially what they call a multispectral mode, where they only send back 70 bands rather than 500 bands, and they sum things to roughly 100 meter per pixel resolution. So it's continuously taking strips and will build up a planetary picture. But those little postage stamps, which I showed, won't probably cover much more than, I don't know, maybe not more than 10% of the planet over the course of extended missions.
First of all, this was a marvelous example of a great astrobiology talk, in terms of you dipped in for the geologist, but you kept it general for the rest of us.
Thanks.
A lot of great information summarized. Liquid water today. You've thought a lot about this. What do you think of the odds, and where should we look for it?
Well, very deeply where you can't access it. The one interest...
How deeply?
On the order of hundreds of meters to kilometers in the equatorial regions. There's places where they do predict liquid water to be present. We don't know if it's actually there or not. It should be, if you can drill deeply enough to get to it. But that's one thing that we do see is the gullies, and I'm not sure how much people know about gullies. They're essentially stream channels on the sides of craters or whatever that have essentially no craters on them, and they've taken before and after pictures seeing them actually form. And there's alternate hypotheses, but I think most people generally sort of agree with it's probably liquid water that forms many of the gullies that we see. And so essentially we think liquid water is flowing on the surface of Mars today. It's not stable on the surface, so it doesn't last very long. So if you identify one of those regions, you can probably access it very close to the surface, if not like just stand there and wait for it to happen. I don't know.
But you haven't mentioned any geothermal possible hotspot where the liquid water would be super deep.
It's possible.
I mean, would we know about that? Are you saying that we can rule out that there can't be liquid water, say, 200 meters, because we made the thermal maps and there just isn't the geo...
Well, it would be tough knowing whether or not you detect it or not. Actually, one thing I do with the Emiss data, it's 100 meters per pixel, and I look basically with myself, but with an algorithm basically looking for hot pixels. And I've covered the surface over and over and over again, looking for that. It's a 1 in 100 chance of discovering something like that, which is probably worth it. It would be a really great discovery, but nothing's shown up. But that's a full 100 meter square pixel, well above the background temperature. And so, at what level would you discover something? I'm sure there's got to be something that exists on the surface that's a hot spot, though.
Oh.
So I'm actually pretty interested in the sources of a lot of these minerals, and particularly Olivi, and perhaps even early stages in hematite formation, sulfate, and what this might mean to what Mars looked like in, let's say, its early Lamarckian period. And Norm Sleep had mentioned that in that very early period, you might have had a short period of plate tectonics, for example. And that would have contributed, for example, to making, let's say, a source of olive, for example. But I want to get your thoughts on the sources of those key minerals. And secondly, how does methane fit into this?
Right. So the sources of the key minerals, I could give an entirely separate talk on igneous compositions on Mars. Not that I understand any more about that than I do about this, but it's what I'm having trouble with, and what I've sort of just realized over the last year with sort of this olivine dissolution stuff is I don't even know where we started in terms of igneous compositions. You have the SNC meteorites, which do not look like much of the rest of the surface of Mars does from the remote sensing. And then you have these very olivine-rich sort of picritic basalts, which sort of fall into the ultramafic category. To be honest, I'm sort of clueless as to what sort of mechanisms you have for forming igneous compositions. And then there's, I didn't talk about it, but there's sort of areas where you have essentially granitic compositions. And how do you, what mechanism is going on to differentiate the, the mantle composition to get such a high silica composition? So yeah, the answer is I have no idea. And then how does methane fit into this? That's also a good question. I don't know that it's obviously important. Everybody links methane to at least the possibility of life. The detections are getting a little bit more confident. At least Michael Mama is starting to look at spatial distributions and other things. But as to, until you actually nail down the source and see exactly where it's coming from, I don't know that you can't just do anything but just kind of wildly speculate on it.
Yeah, I was just wondering if there was anybody has actually mapped out where, if there are hot spots for methane, and do they overlay some other zones of high minerals? For example, the hydrated sulfates.
It would be, they have, like the last Scout proposals, a couple of different teams proposed really, really sensitive spectrometers that would basically zero in on exactly where the methane was at sort of orders of magnitude more precision than what we have now, but we're not there yet. It's just, the question right now is there methane or not on Mars?
Let's take a remote question.
So NASA Ames has a question.
Hi, Josh. This is Dave, and I want to echo the comment. That's a great talk, very, very rich with information and very clear. The question I'd like to ask is this one of difficulty in detecting a lot of these features on the surface. And of course, at the Spirit site, the Columbia Hill site that you mentioned, we witnessed firsthand how atmospheric dust settling just totally covers things up. All those silica deposits now you cannot see anymore, even after we dragged them up with the wheels. So this dust settling is really a major issue, and I was wondering if you could have some thoughts about future orbital missions. How can we beat this problem back? Have you given any thought as to how we can make the orbital remote sensing maybe more effective in coping with this dust settling problem?
That's a good, really difficult question. To be honest, the general feeling that I have, and I think a lot of others have, is typically it's covered with dust. I have to look elsewhere if I'm looking from orbit. I think one thing that helps get around it is, say like the GRS instrument is actually a really good example. Both the neutron spectrometer and the gamma ray spectrometer, they show, things that are buried. And yeah, it's at 600 kilometer resolution, but if you can improve upon that type of thing or find other sort of remote methods of getting at composition, I think that helps. Although I don't know if you'll ever get at the really high level of spatial resolution. So I guess the answer is I don't really know. I don't really have a good sense of what you would do otherwise, other than try different techniques.
Thank you. John, did you have a question?
I just had a question about these seeps geothermal areas. I mean, the fact that the silica deposit was just centimeters below the surface, you could hide anything underneath that below material. It would be just inches below the surface, and you wouldn't know it.
Right. And it's it's disturbing the number of things that the wheels have dug up.
Carbonates. Are there missing carbonates on Mars?
I don't think so. I mean, I can't tell you for sure.
Can you just sort of give a minute or two summary of how you see the situation?
Carbonates seem to be present, like between Phoenix and TES. At least they're coincident with one another, so I think it might gain strength as to being more of a credible detection. But that's, yeah, low levels, but sort of ubiquitous. So where are the white cliffs of Dover on Mars? And we don't see them, which, given what I've been talking about today, you guys might not believe me that I don't think that they're there. One thing that CRISM has talked about at the Mars Science Laboratory workshop is they are seeing sort of what they believe are minor layers of carbonates in, say, the Nili phosphate region. And once again, that's sort of in the area of, well, there's not really, I mean, it's interesting, but I haven't seen enough to say, hey, this is definitive. So if we're starting to detect them in certain places, maybe they are sort of more extensive. But in other cases, like where you have vast amounts of, sulfates, for example, like Meridiani, you really wouldn't expect to see them in those situations.
So you don't see it as a great mystery, given the data that we have, the lack of the white cliffs or something halfway to the white cliffs?
I actually don't see it as a great mystery, although maybe I obviously, when you think of, water and oceans on Mars and things like that, the first thing people think about is, yeah, where are the carbonate deposits? But maybe I'm not thinking about it hard enough, but in my mind it's sort of, well, the geochemistry wasn't right for it.
Well, remember that almost all the carbonate deposits on Earth were biologically deposited. Go ahead.
How about granitic? When you say granitic, do you mean compositionally, and I mean mineralogically and texturally, or are you talking about a gross chemical composition where you get silica mixing with other stuff? I'm
talking about mineralogically. So I can't see I can't see the texture on the surface. I'm just seeing basically the spectral signature of something that's basically composed of a bulk of quartz and feldspar. And even then it starts to get vague about what kind of feldspar. However, that being said, the one thing I argued very strongly about is, okay, you can alter that, you can do various things with it. It may not be a granite, it might be a gneiss, it might have been altered since then, or whatever, but it's hard to get that composition without starting off with a highly evolved magma. So I'm talking about composition.
Oh yeah, if you have a truly granitic rock, I agree with you. But could it be that you just have silica deposited in rocks that have some other compositions, so the bulk composition is equivalent to granite?
No, I guess I would argue against it because, right next to this you have basaltic compositions. And so you have this very nice isolated surface that's composed of plagioclase and quartz. And I can't think of a geological situation where you can mix things in or do whatever without starting off with basically a high silica.
This is quartz, not amorphous silica.
No, definitely quartz, not amorphous silica. I can't tell you if it's K-spar or not, but so I won't say anything very, very concretely about it other than that, and I think that's defendable, though.
Final question, anybody? Yeah, Mark.
You gave a lot of cool examples of minerals or mineralogies that may have formed in the presence of liquid water. You briefly mentioned these nanophase iron oxides as a sort of a reverse constraint. I think you said these things would not be here if water had flown, or if water had been present. So are there, well, A, did I get that right? And B, are there other mineralogies you can point to that say there was no water here and hasn't been for X amount of time?
Right. Well, as far as I understand, as nanophase iron oxides form, they generally form in extremely limited amounts of water. And what that exactly means is not really well known. But, it's not an ocean. But yeah, there's other sort of examples I guess the way I'd put it is there's, it's a desert environment, and you get sort of some oxidation of surfaces, you get coatings on surfaces. These are all sort of indicative of dry environments. And one of the big questions in Mars science when you're looking at these compositions, though, is if you go out to, say, like the Atacama Desert, where it rains once 100 years or whatever, is that the processes are so slow, they're hard to recreate in a laboratory, and they're hard to see on Earth without just the overprinting of that once in 100 years rainstorm. And so what exactly this means about how little water was there is still vague. But that being said, it does mean that, in a relative sense, there is little water there. If you look at like the nanophase oxides, like an oxidized, red soil surface, and you compared it with the phyllosilcates, one definitely screams at you, there's a lot of water here, and this one screams, there wasn't a lot of water here.
Is it olivine another indicator of no water?
Often. That was sort of Phil Christensen's big thing. Hey, there's olivine on the surface, it must have been dry. And to some degree, he's right, but I think you can carry the argument too far as well. Yeah, if you have unweathered olivine sitting on the surface, you probably haven't had a lot of water. But there's unweathered olivine sitting on the surface of the Earth.
Beach sands, for example.
Yeah.
Let's thank our speaker.